The Big Bang Theory is our best explanation of how the universe began. It's a story of incredible expansion from a tiny point. This point, smaller than an atom, contained everything that is the universe today. The Big Bang Theory describes the evolution of the universe from that moment to the present day. The Big Bang wasn't an explosion in space, it was the expansion of space itself. Imagine a tiny balloon inflating to an enormous size. That's similar to how the universe expanded. This expansion continues even today. The Big Bang Theory is supported by a lot of scientific evidence. This evidence comes from observations of distant galaxies and the cosmic microwave background radiation. The Big Bang Theory helps us understand the origin of everything we see in the universe. Understanding the Big Bang is crucial to understanding our place in the universe. It explains where we came from and where we might be going. The universe has been evolving for billions of years. The Big Bang Theory helps us make sense of this vast cosmic timeline. In the beginning, there was the singularity. Picture a point so small, so dense, that it defies our everyday understanding of physics. All the matter and energy that make up the universe today were compressed into this infinitely small point. Time, as we know it, didn't exist before the singularity. Neither did space. The singularity contained the potential for everything, but it hadn't yet unfolded. It was a state of unimaginable heat and density. Then something extraordinary happened. The singularity began to expand. This wasn't an explosion in the traditional sense, it was the very fabric of space stretching and expanding. This expansion marked the beginning of the universe and the start of time itself. From this point of infinite density, the universe began to cool and expand. As it expanded, it became less dense and temperatures dropped. This cooling and expansion set the stage for the formation of the universe as we know it. The expansion of the universe wasn't just a one-time event, it's a continuous process that's still happening today. Imagine a loaf of raisin bread baking in the oven. As the bread rises, the raisins move farther apart. Similarly, galaxies are moving away from each other as the universe expands. This expansion isn't because galaxies are moving through space. Instead, the space between them is stretching. This stretching of space is a fundamental concept in cosmology. The rate of expansion isn't constant, it has varied throughout the universe's history. In the earliest moments after the Big Bang, the expansion was incredibly rapid. This period is known as inflation. Today, the expansion of the universe is accelerating. This acceleration is thought to be driven by a mysterious force called dark energy. The expansion of the universe is a testament to the incredible forces at play in the cosmos. In the first fraction of a second after the Big Bang, the universe was an incredibly hot and dense soup of elementary particles. Light, as we know it, couldn't exist in this environment. Photons, the particles that make up light, were constantly colliding with other particles. As the universe expanded, it cooled. Around 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. This event is known as recombination. Before recombination, the universe was opaque. With the formation of atoms, the universe became transparent. Photons were free to travel through space. This marked the birth of light in the universe. The first light emitted after the Big Bang can still be detected today. This ancient light, known as the cosmic microwave background radiation, provides a glimpse into the early universe. It's a faint glow that permeates all of space. The cosmic microwave background radiation is a treasure trove of information about the early universe. Section 5. A cosmic echo, the discovery of cosmic microwave background radiation. In 1964, Arno Penzias and Robert Wilson were using a large antenna at Bell Telephone Laboratories. They were trying to improve satellite communication. They kept picking up a strange, persistent noise that seemed to come from everywhere in the sky. This noise wasn't from any known source on Earth or in our galaxy. It was a faint, uniform hiss that puzzled the scientists. At first, they thought it might be interference from pigeons roosting in the antenna. However, even after cleaning out the antenna and ruling out other sources, the noise persisted. Penzias and Wilson eventually realized they had stumbled upon something remarkable. They had detected the cosmic microwave background radiation. This discovery revolutionized our understanding of the universe. It provided the first direct evidence for the Big Bang theory. The cosmic microwave background radiation is a faint echo of the Big Bang, a relic of the early universe. Section 6. From simplicity to complexity, the formation of matter. In the first few minutes after the Big Bang, the universe was a hot, dense soup of elementary particles. These particles included protons, neutrons, and electrons. As the universe expanded and cooled, these particles began to combine. Protons and neutrons combined to form the nuclei of atoms. The simplest atom, hydrogen, consists of one proton and one electron. Helium, the second simplest atom, has two protons, two neutrons, and two electrons. The formation of atoms was a crucial step in the evolution of the universe. Atoms are the building blocks of everything we see around us. The process of atom formation is known as Big Bang nucleosynthesis. The abundance of hydrogen and helium in the universe today is a direct result of Big Bang nucleosynthesis. These elements are the raw materials from which stars and galaxies would eventually form. Section 7. A universe of galaxies, islands in the cosmic ocean. Over vast stretches of time, gravity began to shape the universe. Slight variations in the density of matter in the early universe caused some regions to have slightly more mass than others. These denser regions exerted a stronger gravitational pull, attracting more matter from their surroundings. Over millions of years, this process caused gas and dust to clump together, forming enormous clouds. These clouds continued to collapse under their own gravity, eventually becoming hot and dense enough to ignite nuclear fusion in their cores. This marked the birth of the first stars. Stars are the cosmic engines that create heavier elements. Stars didn't form in isolation, they were born in clusters, bound together by gravity. These clusters of stars, along with gas, dust, and dark matter, formed the building blocks of galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter. Section 8. The Accelerating Universe, Dark Energy's Enigmatic Influence. For decades, astronomers assumed that the expansion of the universe was slowing down. This made intuitive sense. Gravity, after all, is an attractive force. The combined gravity of all the matter in the universe should be pulling everything back together. However, in the late 1990s, astronomers made a startling discovery. Observations of distant supernovae, exploding stars that serve as cosmic distance markers, revealed that the expansion of the universe isn't slowing down, it's speeding up. This discovery sent shockwaves through the scientific community. It meant that there was something unknown, something counteracting gravity on a cosmic scale. This mysterious force was dubbed dark energy. Dark energy is thought to make up about 68% of the total energy density of the universe. Its nature and origin remain one of the biggest mysteries in modern cosmology. Dark energy's influence on the universe is profound. Section 9. Evidence for the Big Bang supporting the theory. The Big Bang theory is supported by a wealth of scientific evidence. This evidence includes observations of distant galaxies, the cosmic microwave background radiation, and the abundance of light elements. One key piece is the redshift of distant galaxies. Redshift shows light waves stretching and expanding space. The farther a galaxy, the more its light is redshifted. This indicates galaxies are moving away from us. Another crucial piece is the cosmic microwave background radiation. This afterglow provides a snapshot of the early universe. The abundance of light elements also supports the Big Bang theory. Section 10. The fate of the universe, possible endings. The fate of the universe is a question that has intrigued astronomers and philosophers for centuries. Will the universe continue to expand forever, or will it eventually collapse back in on itself? The answer depends on the balance between the expansion of the universe and the pull of gravity. If the expansion of the universe continues to accelerate, as current observations suggest, then the universe will eventually end in a big freeze. In this scenario, the universe will become increasingly cold and diffuse as galaxies move farther and farther apart. Stars will eventually burn out, and no new stars will form. The universe will become a dark, cold, and empty place. Another possible fate for the universe is the Big Crunch. In this scenario, the expansion of the universe will eventually slow down and reverse. Gravity will pull everything back together, leading to a catastrophic collapse. The universe will end in a singularity, much like the one from which it began. However, this scenario seems less likely, given the current understanding of dark energy. Our place in the cosmos. The Big Bang theory revolutionized our understanding of the universe. It explains the origin of everything, from atoms to galaxies. We are all made of stardust, forged in ancient stars. Our atoms were part of a giant cloud that formed the sun and planets. Our planet is just a tiny speck in the vast cosmos. The universe is full of beauty, wonder, and mystery. The Big Bang Theory shows the power of human curiosity.